Bridges are an extremely important structure, globally used predominantly to assist traffic to cross various hazards. The overall successful design of a bridge is essential for the safety of individuals using it as well as the people or other structures surrounding it. To create a safe and structurally sound bridge, many elements are necessary for consideration. Some of these elements include the materials used, the quality of construction, the amount of force on individual sections, the external loads, and the location of the bridge. The task is to design and construct the lightest possible bridge capable of supporting the greatest possible load, made completely from spaghetti and superglue. Potential designs will be discussed, analysing existing bridges and how elements of these bridges can be used to create this spaghetti bridge. A step-by-step method will also be included outlining how the final bridge will be assembled and what was changed from the test bridge. Additionally, a detailed analysis will be included on the issues faced throughout the process of design and construction, with a breakdown of how improvements could be made if the process was repeated. Bridges are a structure primarily used for traffic and make it possible to cross many obstacles such as a river or valley. Different types of bridges have different functions and different ways to carry loads. There are 5 major types of bridges so used around the world. These types are the beam bridge, the truss bridge, the arch bridge, the cable-stayed bridge, and the suspension bridge. The beam bridge is the simplest structural bridge which is supported by a pier or abutment at each end. The truss bridge is a truss structure comprising of triangles in a truss shape. The arch bridge is constructed with abutments at each end and shaped as a curved arch. The cable-stayed bridge has one or more towers from which cables support the bridge deck. The suspension bridge contains a deck which is hung below suspension cables on vertical suspenders.
For the design, specific structure is needed to strengthen the bridge to carry a greater load. If the beam bridge design is chosen, our bridge would be a single beam model and it could not carry a large load, meaning the beam bridge is excluded. The cable-stayed bridge and suspension bridge would be better utilised across longer spans, which is not appropriate for our bridge design, as the size of the spaghetti bridge constructed would be approximately 400 mm long and 80 mm wide. In terms of technology, these two kinds of bridges would be very difficult to construct with only using pieces of spaghetti, as it cannot be used as a substitute for the cables, as it is rigid and contains no flex with very low strength when placed under tension. The 2 remaining bridge types are the arched bridge and truss bridge. The arch bridge is extremely strong, but spaghetti cannot be bent into the shape of an arch, so the arch can only be made by joining several pieces together. The truss bridge utilises the strength of the triangular shape, so it's very strong. Finally, we decided to combine the advantages of the arch bridge and truss bridge and use both arch structure and triangular structure to build our bridge. Therefore, our final bridge has an arch outline and triangular structure within. Spaghetti is quite strong in tension but weak in compression, so we tried to make spaghetti take the tension so that we could maximise the advantage of its property. We made the compression members as short as practical. We used Sky Sieve to model our spaghetti bridge to gain knowledge on the maximum loads that our bridge will be able to carry. From the picture shown, it can be seen that the bridge is loaded with 6 kilograms, and this is the result. A simple test was undertaken, which involves binding together a bundle of spaghetti strands with tape on either end and placing the beams across an open space. A cup is then hung from the middle of the beam with weight added slowly. From this test, it can be seen that strands of spaghetti that were along the bottom of the beam, the ones in tension, are the first strands to buckle under the load. This test demonstrates the necessity of ensuring that the beams of the constructed bridge are not placed under too much tension to ensure that a failure does not occur. The test bridge and final bridge were constructed over several days in what was a frustrating and timely process. The materials used were spaghetti number 3 and Sally's Quick Fix superglue. In building the test bridge, several things didn't work very well and were then changed in the building of the final bridge. The first step that was taken was to draw out on a piece of cardboard our design so that it could be accurately followed. It was imperative the drawing and measurements were exact to ensure the bridge was the right length to fit across the testing piece. This was done using a ruler and a protractor. The next step was to take 3 individual pieces of spaghetti and stick them together. The 3 stuck together pieces were then stuck to 2 other bunches. This meant that the beams were made up of 9 individual spaghetti pieces stuck together. Old beams in the bridge were made the same way. Assembling the beams into place started by gluing the bottom long beam together, which overlapped to add strength. The inside beams were then placed and glued. Once these had both dried, the outside small beams were cut using a sharp knife and snapping technique to stop the spaghetti from cracking. The beams were cut to fit into the circular outer and glued in. All these steps were then repeated to create the second frame. The 2 frames were then glued together with small beams in between them. It was decided that the best way to do this was to place a box in between the 2 sides and a box on top to keep pressure on the beams and keep them balanced. Beams were then placed and glued into the bridge to add strength to the structure. These included cross beams on both sides of the centre of the bridge, a cross beam on the centre at the top of the bridge, cross beams on the inner beams of the bridge, and beams at the bottom corners of each side of the bridge. Testing of the spaghetti bridge was conducted on Thursday the 4th of October on the testing apparatus which measured the force applied to the bridge. This apparatus was connected to the metal plate which was placed on the centre point of the bridge, dispersing the load evenly. By winding the handle seen above, a downward force was applied to the centre of the bridge through a chain attached to the metal plate. As this force was applied, the beam along the bottom of the bridge began to flex and reach approximately 5 kilograms. However, the threaded pole on the handle reached the bottom and were not able to reach failure. The apparatus was then reset with a shorter chain attached to the metal plate, and the testing continued. When this test commenced, the beams began to flex again. However, this time the upper sections of the bridge began to twist. The bridge held approximately 6 kilos before these upper members began to separate at the superglue joints. As our bridge weighed 175 grams and carried 6 kilos, our load to weight ratio was 34.29.